So Andy Mitten, he's a practicing structural engineer and partner in the Vancouver-based structural engineering firm, Bush Bowman Partners. For almost 40 years, he has been the design engineer on several buildings and bridges, including the Vancouver International Airport and the US terminal in Nassau, Bahamas, and the SkyTrain Fraser River crossing at New Westminster. He also wrote the book on the structural design for Canadian buildings, which is used both by EITs and undergraduates, and he's a graduate from British Columbia with a bachelor's and a master's degree. With that, I will hand over to him. So you can share your screen.
Let's see, how can I actually do that? Oh, okay. There we go. And from the beginning, there we go.
I love steel, and there's many wonderful things that can be built, and YVR is just one of those examples.
Andy and his team of structural engineers are in charge of designing, documenting, and overseeing the construction components.
I don't think we can see the screen yet.
80,000 square foot domestic.
Can't see the screen. Okay, what have I not done right?
So you want to share it again?
Share screen. There, this one. There we go. There we go. All right.
Yeah, there.
That's
awesome.
it.
Okay. Good. We're good.
I love steel, and there's many wonderful things that can be built, and YVR is just one of those examples.
Andy and his team of structural engineers are in charge of designing, documenting, and overseeing the construction components of YVR's new 280,000 square foot domestic terminal area.
It's a little noisy here. We're at the west end of Pier B, which was the first part that they started building, and it'll be the first part to open.
So why is steel so important? Not only is it one of the strongest materials, the contemporary design and steel structure will help create a large, open, and visually unobstructed experience for retailers, passengers, and employees.
So if you look behind me, you'll see the main large cruciform columns that provide the stability for this structure, and those are all infilled with over 4,000 beams to support the floor and roof levels.
We've spent over a year doing detailed design, and then we've spent quite a lot of time actually in the field doing work. We review shop drawings, and there's literally on a project of this size, thousands of shop drawings to be reviewed.
But a project of this magnitude requires help from hundreds of people. And today, everyone involved in its construction, including YVR's board of directors, senior executives and project managers, as well as the construction contractors and airline representatives, are all on site to celebrate the lifting of the final beam into place.
What we want to stress is that this is a team effort.
We'd like to thank Bush Bowman's team of engineers, as well as everyone else who has helped bring the AB Pier Connector to fruition. Stay tuned for the next video, where we'll take you behind the scenes and show.
All right, so here we are, and go on to our real topic, which is structural design of Gerber Cantilever system, filling the knowledge gap. And this is a talk that I originally gave just over a year ago in Montreal, back before COVID, and it was at the SEAL conference, and it was at the invitation of CISC to go out and do it. And so this is sort of seems to work well as a reasonably short talk. So the Gerber framing system is a very popular roof framing system in which you have cantilever spans and a drop-in span, and it's usually used only for roofs. And the aim of it, it was invented in the mid-1800s or early 1800s as a good solution for bridges, and it's more economical. And this is one bridge that uses its system. Took them about 3 buildings of the bridge to actually finally get it built. But so that you have this drop-in span in the middle and these 2 large cantilever spans which go out and pick it up. So the advantage of it, the drop-in beam can be smaller than if standard framing. The cantilever moment reduces the moment on the interior span back here. And finally, the interior span deflections are reduced by continuity. So you get a lot less of your beams being controlled by deflection. Disadvantages are it takes a lot more analysis to design, and you need to consider the stability of the cantilever beam out here. Otherwise, you get into some real problems. And a lot of this, I'm going to follow through an example of one where the Gerber framing system didn't go very well. And this is the Gerber framing of Station Square. And this is the result of it. And this is the opening day of a grocery store in Burnaby, which is a suburb of Vancouver. And it happened, here's downtown Vancouver, there's Station Square, there's YVR for kind of orientation of where this occurred. And so what happened with this was that there was a buckling over of the cantilever beam. This is the same beam in this photo as in here after the removal of some of the material. And it happened at 9 a.m. on April 23rd. And the customers were let into the building. It was pre-internet. There wasn't a huge amount of entertainment. So there were lots of people. It was Seniors Day at the store. And there were lots of people there. The mayor was there to open it. Fire chief was there. And within 15 minutes of that opening, the roof had collapsed with cars in the produce department and a variety of other things like that. And so the collapse was on a Saturday morning. And on Sunday morning, our local tabloid paper, which is very similar in many respects to the Edmonton Sun, had a solution of how you're supposed to design these Gerber girders and how to put the stiffeners in and the bottom chord extension. And so, you know, all these nice diagrams. Unfortunately, this is the sort of stuff that really doesn't get taught very much in school. And I think still, and I may get corrected here from U of A, but certainly from UBC still is not something that's taught very much. And this was a real big deal in Vancouver. There were lots of concerns about, you know, the safety if a brand new building can collapse like this. Unfortunately, nobody was killed. There were a couple of people that were injured, and the amazing thing is that, and this report's available through the internet, is a variety of these photos that really you shouldn't take. And I tell my students, you know, if you ever get a chance to take a photograph like this, don't. Run out of the building as quick as you possibly can, because the roof's just about to come down. And you really don't want to be standing underneath that roof while it comes down. But fortunately, and partly because the fire chief was there was a realization that something was going wrong. And what the first trigger for this indicating that something was going wrong was that the sprinkler pipes sprung a leak. And they with this beam twisting. And I know one of the 2 people that worked in the store who were tasked with the job of going and mopping up where the sprinkler was leaking. And so they went out and started doing that, and they looked up and they said, hey, we got to get out of here. And fortunately they did. So there have been other similar failures. This is one stolen off the internet of one in Texas. And these were sent to me by Michelle Como of Campbell Como Engineering in Halifax. And this happened during a very heavy snowstorm in Halifax. And what you'll notice from all these is they all have an incredibly similar photograph here, or a portion of a photograph. We've got a girder cantilevering over, right? Both cases here, a little bit harder to see here, but there's no vertical stiffener here. And they've obviously collapsed over and done unpleasant things. And the roof has collapsed in all three cases. So, there's obviously something going on here, which is a consistent reproduction. And the challenge with the Gerber framing system is to figure out, the fundamental equation of structural engineering is your factored resistance has to be greater than your factored loads. And, how can you figure out what the resistance is so that you don't get this? You can probably figure out your factored loads reasonably easy, but if you're not sort of following all the failure mechanisms, how can you figure out your factored resistance? So let's do a quick review of stability and sort of a points, stability points. Sorry. Okay. All right. There we go. Stability point number one, slimmer members in tension don't buckle. So if I have something in tension, it doesn't buckle. If I try and put it in compression, it's not a happy camper and it buckles, right? So that's pretty obvious. The result, though, is that if you don't brace the tension flange, if you brace the tension flange, you don't brace the compression flange, you really don't do much to help your unsupported length. So the problem with the Gerber system is that you have, this is your bending moment curve, or this is your bending moment curve, and it moves back and forth. And these, what I've drawn here is the green lines represent the top flange compression or tension state. Green being tension, red being compression, and the red ones are the ones that are trying to buckle. And here's where you've got your supports. You've generally got a support top and bottom flange at the column, and you've also generally got supports across the top flange here, some of which is in tension and some of which is in compression. And stability point number two, your unsupported length reduces the capacity very quickly as the distance between the support points increases. So I can put more compression on something that's short than I can on something that's long, right? And that is also true for beams. If we have an unsupported length of a W410 by 39, as we get further and further out, the moment capacity of that beam starts to drop dramatically. And so S16 does a great job of covering laterally unsupported beams that are, and so we've got our tables, our blue tables, which we refer to, and we can figure out our moment capacity and figure out curves like that. Stability point number three is that the unsupported length of a member can actually be much greater than the length of the member itself. And the way to illustrate this is what we have with a column that's pinned at the bottom with a point load at the top. Your unsupported length, or your K value, is 2, and so there you've got an example of how the unsupported length is actually longer than the member itself. Stability point number 4, inflection points are not necessarily points of lateral support. The inflection point not only can move, but it's really not a point of lateral support, and it can move laterally and not resist lateral movement, which is what you're trying for at a point of lateral support. And the other point is that if you brace one element in compression to a similar element in compression, it just makes both buckle the same way. So if we've got, if we put, a compression flange here and a compression flange there, unless there's a load path from where it's trying to buckle laterally to the end, we wind up with them both just going in the same direction. And this was illustrated very well by this project from Edmonton, which I'm sure you folks are all very familiar with. And stability point number 6, the force required to stabilize an element is not large. It's about 2% of the force, but you do need to have that support in there, and it does need to have a load path so that it can't move relative to these points. If it moves in the middle here laterally, then you no longer have a point of support. So the stability of individual elements typically are roof beams. If it's attached to metal deck, we're going to have these supports here. These are pins added here these days. Used to be welds in our part of the world. You may be still pins and welds in a lower seismic area, but in our typical Gerber Girder situation, we have the open web steel joists. So this is our point of support, and that's our point of support. We don't have a support for the beam in between those places where the joist is attached. And if our beam is only partially restrained by the diaphragm, we do have our diaphragms up here, our connection points here, and I've drawn in green where our support is for that top flange. And cantilever beams can buckle if not controlled. And what the code says and gives us is for cantilever beams, we need to do a rational method of analysis, taking account of the lateral support conditions at the support and the tip of the cantilever. So what we have is this nice little diagram, which was a 1989 CISC publication. And I believe U of A and Laurie Kennedy had a lot to do with producing this. There was a lot of reactions to the 1988 failure at Savon, and this was one of those reactions. And this is now quite difficult to get. It is available from the AISC website, but hard to get on the CISC website, despite it being a CISC publication. And restraint conditions, this stability criteria for metal structures, and I really like the 5th edition because it seems to cover this a bit more than subsequent editions. But you have the sort of restraint conditions at the root and the tip of the cantilever, and what an effective length is here. And what we're seeing here is we can get up to some very high values of our effective unsupported length being much greater than the length of the that's unsupported. So our stability of our Gerber cantilever, we need to provide lateral restraint to both beam flanges of the column, provide lateral restraint to at least the top flange of the cantilever at the tip, and provide web stiffener at the column. So this is a checklist that we should probably go through on these. And there's lots and lots of examples out there of Gerber girders that are not with all those 3. So this is a beautiful beam column extension. Beam column, there's a joist extension at the bottom here. They have a vertical stiffener in here. They've kind of gone to town with it here, providing 2 vertical stiffeners. That's not very common, but they have a vertical stiffener here. And the joist connects at the top of the column, so you have support for the beam at the top and the bottom. And so the not quite as happy at the tip. What we see here, this is an electrical conduit, so it doesn't play a role. We don't rely on electrical conduits for lateral stability. And so what we've got here is the beams going over, and the first joist is back here on the drop-in span. So the drop-in span itself is has quite a distance that's unsupported here at the top as well. And of course, the distances between the joists here are unsupported. So if we were to determine the K for the cantilever on this one, what we'd see is at the root of the cantilever, we've probably got support top and bottom, or we do have support top and bottom. If we look at the tip, we're probably not supported at the tip. So our top flange loading gives us 2.5 times the length. Our other cases give us about 1 times the length. So which K to use? 0 top flange load. There's no loads on the top flange of our girder up here. It's all coming in through this fish plate at between the beams. So what we see, we probably have a K of 1. If we go look at the this nice table from that was produced by CISC, we see this is kind of our situation here. We've got tip has lack of support, and we have our first joist is sitting a little ways back, and they're recommending K of 1.5 to 2.5 for that. So somewhere along the line, we've got a K of 1.5 to 2.5 or a K of 1, and that we can evaluate it from. So my take on this is you probably want to go with a conservative value of K provided by the guides, and I'd go with probably 2.5. And stability really shouldn't be a numbers issue. And you want to provide the positive stability where it's required. And some engineers like to use a K of 1.5 on cantilevers regardless of anything else. So, and you should definitely use a higher K where it's appropriate. And it's a little bit like playing hockey. The other team has the puck. They're in the end zone. They're trying to score. You want to get that puck away from the net, right? You don't want to be looking around like this poor goalie here from the Montreal Canadiens who's looking for where is that puck? It's somewhere in my end zone. I don't know where it is. Is in my net. So there's 2 cases where you're getting the high K. You're evaluating an existing building without sufficient stability helpers, like they don't have the bottom chord extension, or they don't have the stiffener in here, and go with a high K that, and there is you want to be you want to be as conservative as possible and not give the building the benefit of the doubt, because it doesn't deserve the benefit of the doubt if it doesn't have these stability helpers. And the other one is you're designing a new building, and if you've not added in these, then maybe you should be doing that to get your K down. So I'm all in favor of using a high K for that when I'm evaluating this. So this one here, if I was doing this, I would be looking, I see what this one is. I have no vertical stiffener in here. I have no support on the tip, and I'd probably use a K of 2.5 in that case. Go edging to the higher numbers because of no vertical stiffener in there. Again, this one here, and this is, and these examples are from pre-1988. And after 1988, the Gerber systems all incorporated the stability helpers. But in Vancouver, prior to that, it wasn't that common to have all those things in. And you would sometimes see examples like this, where, you know, at the column here, we not only have no stiffener, we have no support at the bottom. And at the top, we're kind of got a support at the top by having these bridging between there and there. So, you know, you've got a partial stability at the top, maybe this guy here, but probably not even very good. I have no stiffener, and I have nothing at the bottom. At the tip, I don't have anything really here coming in or supporting it. I have this sort of a ways back from the tip. And so I would be inclined to use, and I have some top flange loading, and I have some loading that's not top flange loading. It's coming in here. So I'd be inclined to use a K of at least 4 for this. I'm probably leaning more towards the 7.5. So cantilever originally connected at the root. We're up here. and the tip here is totally free. And although you might argue that we are connected here, on the other hand, it's a glass diaphragm, which I'm not really that inclined to believe is actually a diaphragm. So I would be inclined to be somewhere up here at the 1.4 L going from that way. So in S1619, we've managed to introduce new requirements for flagpole cantilevers, which would be this sort of thing where warping isn't possible at the root. And so that's will help to, analyze these sort of things. So now how to design a Gerber Girder system, and which is the sort of main aim of this, because one of the things that I fear is that the lessons of the save-on failure are getting less and less common, particularly away from Vancouver. In Vancouver, there was a variety of knowledge that came from it, and the older engineers that are kind of my vintage, I think I was an EIT at the time, or maybe it was a PEng, but it was quite a while back, that we're all kind of heading for the door and retiring or worse. And so I worry that this knowledge isn't getting passed down. So we designed the drop-in span, and that should be a real easy calculation. It's like any other beam, except for it's being a roof beam, so you have to think about the uplift at the same time. So we have to examine two cases for snow load, in which we take our 100% and our 50% snow if it's a snow loading. And if it's a live load, then we have a different sort of skip loading. So our live loading on our cantilever, if we load on the cantilever, there's a point load here, it gives this bending moment. If we load on the back span, it kind of gives this bending moment, and we put the two together. So we get the skip loading to give maximum positive and skip loading to give minimum positive, which can actually do this rather dangerous thing here where we have our bending moment curve provides no region where the bottom flange goes into compression. So, or into tension, sorry. And so this is the sample one. We're winding up with our bending moment here. And as you can see, depending on our skip loading, we can influence where our point of inflection is here, which, while it not being a point of support, the greater length between in compression here does make it more or less stable and make it more likely to laterally buckle. So we want to compute the cantilever moment. And so then we're going to use our K of 1.5 in this example and have a look here. So here's our cantilever moment. I have a moment of 368. I'm going to use, and I'm supporting here at these points. And you can see here, I brought down where the flange goes from red being in compression to tension over here. So our stability points here are helpful. You can see how important it is to add a stability helper at the column load here, where we are definitely in compression on our bottom flange. So on station square, and these are taken from the inquiry results, and what we saw on station square was that it was actually live load due to parking on the roof. And with that beam, there was an awful lot of the beam was in compression. And don't forget, in station square, there was no bottom chord extension here. So if we do we need to design the backspan, and I go to this handy dandy book here, and Stability Design by Theodore Columbus, and the interior inflection point's not a brace point, and we need to consider the different load cases, and we take account of the stability. But this is where we've got our stability, is these nice little X's, and here and here. And so we do a final check and we make sure the details are happy. The bottom chord joist extension in, top chord joist extension in, hopefully. You got problems if it's not. And a vertical stiffener in at the column. So what matters, number one, provide positive bracing at the column, top and bottom. Bad Gerber here, good Gerber. And what matters, number two, provide a web stiffener at the column, bad Gerber, good Gerber. And the web stiffener is really, really important. We probably wouldn't be looking at these photographs if there had not been a missing web stiffener in here. If the web stiffener had been applied, these photographs probably would not exist. This one here, part of the building was a subsequent addition, very similar sized beams. They did have a vertical stiffener. The other part of the building did not collapse. This part without the web stiffener did collapse. What matters, number three, provide bracing at the cantilever tip. So we got bad Gerber here, good Gerber here, where there's a support out towards the tip. And so what matters? You want to do the appropriate pattern loading. And not matters number two, you want to use the cantilever span using the appropriate K. And you want to check the interior span, remembering that inflection points are not brace points. And you want to really watch out for this sort of behavior where you're entirely in negative bending throughout the entire length of the backspan beam under some skip loadings. And what you can do to control that, you are the designer, you can control how long your cantilever is and maybe bring this back a bit so your cantilever moment drops down. Then you start to get to be sort of more like your blue shape here, which is much more. So hopefully the foregoing gives you an indication of how to design a Gerber girder system. It's brief, and there are references that you can go through to kind of have a look through to see how to do it. But put yourself back into 1988. Put yourself in the designer's shoes. You're a young EIT. You've recently graduated. You're working in a busy structural engineering office. You've been given the job of designing the roof system on a supermarket. And you're going to design a Gerber system roof because that's what everybody else does. And Gerber framing and cantilever beam stabilities not being discussed in your university classes. And nobody's trained you how to do these designs. And I know that because I went through the same university and was taught by the same lecturers as the young EIT that did this. And it was not a subject that was covered. So this was S16 M78 before Save On Foods. And there were no special flags for cantilevers, no mention of Gerber framing using this edition of the standard. And it would not be unreasonable to assume that a cantilever beam was just like any other unbraced beam. So what does it now say about it? There's no mention of Gerber framing in S1614. They add bracing top and bottom flange at the end of cantilever beam unless otherwise accounted for in design. And so if we look at it, what they want you to do is a rational analysis, and cantilever beams, rational method of analysis take account of lateral, torsional buckling restraint conditions supporting the tip and the flexibility of the backspan. You're not quite sure what is all this about. So you go look at the CISC references. This book here tells you no stiffener at the column. It's not shown. Stability is not flagged as an issue with this example of a Gerber system. And this was basically what was around at that time. And so what does your design look like? Do you know to add the vertical stiffener at the column? There really doesn't seem to be much guidance that it should be there. consider the stability of the cantilever and use the correct unbrace length. Is that likely to happen in your design? And are you going to consider the stability of the backspan and figure out the unbrace length? You really don't have much guidance in how to do it, and everybody else in the office is kind of busy, so you just kind of go and look at it from the way that you've looked with sort of other beams. So now put yourself in 2017. You're on the S16 committee, and there's no specific Gerber causes in S16. And this is the most common framing system in North America. And should you add a Gerber system framing requirements to S16? And option number one, do nothing, keep the status quo. Everyone should know about this by now anyway. And some people were saying, you know, this was all covered sufficiently in school, and the variety of people that were on academics were kind of looked at each other and said, well, I'm not teaching this. I'm not teaching this. So that's probably not a great solution. Provide warnings in the code and methods of analysis in the commentary. At least you get a warning. Or option 3, provide methods of analysis and formulas in the code, which is difficult to do, is that it's really hard to get closed form formulas on this. So what happened, the 3 options kind of got kicked around for a long time. And in S1619, we've added 3 new flags. Flag number A, look after the cantilever and make sure that it's happy. And B, look after the web at the column, adding the stiffener, much like our equivalent of the Edmonton Sun told us to do the day after Savon fell down, and look after the backspan. So we've got to do, and this is one way of doing that through the Galambus's book. And S1619, anticipated new material on CISC, design module 3 on Gerber roof girders. And it basically has lots and lots of tables. It has about 500 pages of tables that go through this, provided that you're within the design parameters. So it takes account of lots of things that we should be taking account of. It takes account stability of the cantilever, stability of the backspan, variety of different magnitudes of snow load and wind load, skip loading for snow load and live load, wind uplift, all the things that we really need to be taking account of. But it also has a variety of restrictions. So it's got a flat roof, which often isn't the case because there's maybe some areas of 2-story or greater. So no stow drift or significant roof loads in the span, all the bay lengths the same length. I wish I could convince architects to do that. All bays the same width throughout the line of the girder. Again, I wish I could convince architects to do that. And all cantilevers the same length. Vertical stiffener at the column, so it doesn't really help you if you're evaluating one of these existing buildings. Joists on the column line, and provides lateral paint on the top of the column, which I think is a great plan, but quite often not fully covered. Have a horizontal brace, top of the column, bottom flange, the beam at the column. Dead load less than 1.3 kPa, so it doesn't work with concrete on metal deck. Live load 1, so the tables don't work for parking on the roof. So there's a variety of reasons why you couldn't have used this module for looking at the Save-On foods. And it's got some examples, and you pick out this. And what the aim is that the that it gives you a preliminary design for designing this, and it is stated that it is a preliminary design. And I think really what needs to happen is maybe this gets combined with this, and then you can sort of see what happens when you get away from the situations where you're not fully covered by the tables that are in here. So back to Save-On Foods, issues during construction. So during construction, there were lots of concerns. It was a very lively and bouncy structure. There were lots of the concerns raised by the contractor. You know, every time he would have equipment up on the roof shook around and did lots of bouncing, and people would be standing out there and it'd be bouncing up and down. So an independent structural consultant was hired to review the design. And what happened, the stability issues were missed by all the engineers involved, those that designed, those that reviewed, and MSS found that the beam was overloaded and agreed by the designers. And that was agreed by the designers. Everybody agreed the beam was overloaded and remedial action was recommended. So what they did was they went and looked at mill certificates, and they found that the yield of the beam was higher than specified, and that the review engineers and the design engineers concluded that with a higher strength beam, the beam capacity was sufficient without the upgrading. So, okay, it's all good. It's all happy. You can proceed. You don't need to do anything because our mill certificates are good. So the problem with mill certificates is that beam resistance formulas are based on a specific yield, specified yield for the grade of steel. And they typically expect the mill certificates to be higher than specified. And due to residual tests, you know, where it depends where you're going to take them, take the certificate. And the other thing that's a problem is that we've totally missed the stability issue here, which is the main cause of the failure. So how S16 covers now tells you you're not allowed to use the mill certificates, increase the capacity of the beam. And this came out basically the next edition of S16 after 1988. So this was 1984, no mill certificate warning. There wasn't anything that flagged it there. And 2014, not allowed to use mill certificates to increase the capacity of the beam. So next problem is who should call up the stiffener and the joist extension, which was another issue. And there was some confusion as to who should be calling it up, the design engineer, the detailer working for the fabricator. And the bottom line is both should be called up by the design engineer. They're a fundamental part of the stability, and therefore you need to be calling up your tie joists here and your stiffener. And I will show another example of who should be calling up things in a minute. That's also a gray area. So there was lots of confusion with that. And the results of the failure, they actually, when they were detailing the building, they did contact the design engineers and say, we suspect you left tie joists out of here. Do you want tie joists? And by the way, it's an extra. And the answer was, no, we don't want tie joists. So the decision was posted to put in the tie joists, and it was left off. So result of the failure, both Tam Tacey and MSS go out of business, all staff laid off, engineers involved from Tam Tacey and MSS are disciplined, and their licenses lose their practices. A lot of the work was done by an EIT who didn't have a license. And it did have an effect on his career. On the other hand, it was the engineers that were supervising him that did wind up losing their licenses. So inquiry into the roof collapse. There was a provincial commission was called, and there were found several challenges in the design. One of them was that the loads were wrong that were used in the design, and they had increased as the design proceeded. The contractor come back and said, well, I'd actually rather just place this all as concrete. Any problem with that? And so what used to be insulation got replaced with concrete, and changes in loads weren't reflected in the design. And there were lots of issues with the beam resistance calculation. And it resulted in a lot of concentrated research on Gerber framing and engineering education. And my theme here is, unfortunately, a lot of that has faded away. So there were also concerns about the construction industry practice, fast tracking, creating more chance for errors, bidding professional services, and fragmentation of contractual responsibility. And there were desires to have minimum fees so that professionals were chosen on merit and service rather than fee driven. And lots of these things are still part of the way we do business these days. So there were increased emphasis on checking. And so what happens is concept reviews are now a mandatory part of the design. And I spend an awful lot of my time doing concept reviews on designs that have been done by other engineers in our office, and a lot of our much more emphasis on checking in there. And the experience required for a structural engineer went from 2 years when I was registered to 4 years, and increased emphasis on additional information. And the Struct-Eng program was introduced, requiring a minimum 10 years of experience and mandatory continuing education to keep that. So the Struct-Eng was supposed to be BC wide, but it's only mandatory in about 3 or 4 municipalities, including Vancouver and a variety of others, including Burnaby. So continuing education for structural engineers, codes change, how do you keep current? Subjects such as this, how to do that. And what happened was there was a continuing education program started with evening courses for structural engineers in BC, and that's grown to quite a comprehensive program. So that was the end of my talk in Montreal. And then it sort of ended, and there were questions, and there was a really active discussion and very, very active on what to do about bolted connections at the ends of the joists. And what there apparently in Quebec, it's a requirement that joists be bolted to the flange of the girder. They can't just be welded down later. And so so you result in 2 holes here. And we sometimes see that in Vancouver as well. This is on a simple span, not on a not on a Gerber girder. So I've drawn in red the compression flange up at the top and green the tension flange at the bottom. So these are occurring in the compression area, and they're 17 millimeter holes. So do the bolt holes affect the capacity? And what S16 says, and this is actually taken from S1619, and section properties need not be reduced to account for the presence of bolt holes when either the holes are in the compression zone only. The holes are standard size holes filled with the correct size bolts. And or you have this other option where you've not exceeded 15% of the gross area. So 17 millimeter holes, 5/8 bolts to secure the joints, the bolts in compression, so no worries. But how about if we have our tension zone here, our green in here, and we've actually got our peak moment right at our column, and we're asking there to be a joist right at the column for stability. So there's going to be 2 bolt holes right in the flange, in the tension flange, right at our critical section. So let's say we have a Gerber girder, W530 by 74, and we're going to come with 2 5/8 bolts like that other shop drawing. And we're reducing by 20%. So it doesn't work by that clause. It also doesn't work by if we go through net section. So, and if you kind of look at this, maybe the 15% is generous. And you may actually wind up with a net section failure with 15%, but that's probably due to the fact that you're probably relying on the fact that your mill certificates are showing that your strength's a little bit better than you're specified. So if we look at our different hole sizes, if we had a 1/2 inch hole, our minimum flange width is 186. The problem is that the beams that we're typically trying to go for here are the beams that are at the top of the beam selection table, and they all have quite narrow flanges. And the wider flanges tend to be the ones that are down lower in the table that we're not necessarily going for. So in theory, in these beams here, up to a 610 by 82, which is quite a chunky beam, especially for a Gerber girder, we can't even use these half-inch bolts in these. So the next question is, if the bolt holes do resist the capacity, who should fix this issue? Is the engineer who's should have oversized the beam based on assuming bolts? The detailer should tell the fabricator to add extra plates and help the beam, or the joist supplier should just use welded connections. And my take on this, and this is kind of where we're going in our office, is so we should probably be accounting for the possibility of bolt holes for joint fastening and state the maximum size of bolt holes that can be used in the drawing, and say that if bolt holes larger than that are used, then the beam shall be strengthened. So one way is to, rather than go with one of these beams at the top of the section, go further down and use a beam with a wider flange, and then off you go, and you can go and produce it wide. And again, I'm still saying that you should specify your maximum bolt size on the second one. So the next way, select a beam with sufficient capacity such that the next section works, and you can wind up doing that. That would be another option. And so bolt holes in the tension zone do make a difference. They can govern the design. And part of the interest in Montreal was that there had been a failure of a Gerber girder system by tension tearing at the bolt holes. I'm trying to get a photo of that and haven't managed to. It would really improve this talk. So, and you probably want to state the maximum bolt size. So what really went wrong on Save On Foods? Our most important equation in structural engineering, factored resistance greater than factored loads. The factored resistance was lower than expected because the stability failure was not considered. And the factored loads were higher than expected because of calculation issues and changes by the architect and the contractor. So thanks for being here. Any questions? We've just about finished on time.
Awesome, lovely. Thank you so much, Andy. Everyone, if you have a question, just feel free to unmute if you'd like. You can click the raise hand feature or just type your question straight in the chat, whichever works best for you.
Thanks.
Oh, we have a question from Michaela.
Hi there. I just had a question about structural engineering in BC. So can you not take a structural engineering degree just in the 4 years at schools there?
That's a good question. I think our duration is pretty much the same as most other universities. There's 3 universities that are graduating structural engineers now. UBC Okanagan, UVic, and BCIT, and they all have a 4-year program, and you come out as an EIT, and with your basic bachelor's degree and knowledge of how to do structural engineering. The challenge is that because of accreditation rules and lots of other things like that, it's very difficult to have as much specialization as was done in maybe the old days. UBC used to be a 5-year program, so you did 4 years of engineering after 1 year of usually first-year sciences. And in addition to that, UBC was kind of in the words of one of the materials profs at UBC in my vintage, was a structural department masquerading as a civil engineering faculty. and which was great if you were wanting to do structural engineering. Wasn't so great if you were wanting to do other things like maybe concrete materials and things like that. So or construction and variety of things. So the answer is that you do wind up getting the same bachelor's of civil engineering with a structural specialization in BC as you do elsewhere, but it's really, engineering is really an apprenticeship, and it's in your first 4 years to getting your PEng that you will wind up getting a lot of that apprenticeship, hopefully working for a firm that's going to be mentoring you and looking at your designs and saying, hey, have you thought about this? And by the way, there are problems with Gerber girders if you don't put in the stiffeners and things like that. So, and then after you've got your PEng, then you do a bunch more time and hopefully some more experience. And then you write some exams and you become a struct-eng. And so to sign and seal drawings in such municipalities as, or cities as City of Vancouver, you need to have your struct-eng for structural, not just your PEng. And of course, that's not, the struct-eng isn't something that's transferable. So if you had your Alberta PEng, you can't arrive, or your Ontario PEng, you can't sort of arrive in Vancouver and say, okay, I'm a struct-eng in Vancouver and I can sign and seal drawings in Vancouver, which is a bit of an issue. So any other questions? So is Gerber girder, I've got a question for you folks. Is Gerber girder's framing covered in your courses at U of A? Bob's smiling.
We have a hand from Robert as well.
I had a different question, but I'll answer that. We talk about it in both cases, but not nearly enough. So, I think especially for the graduate students, we should probably amp it up a little bit for the reasons that you stated.
I think if you go into most, like you go into the big box warehouses, the Home Depots and the IKEA, and back when we could go into these and you're wandering around and looking up and there are old Gerber girder systems, right? And there's lots of opportunity to take good photos of Gerber girder framing. We were in Bob, the S16 committee. We were having a nice meal in a restaurant in near where we were having S16 meetings. And we were looking up, and there's a Gerber girder system, and oh, does it have a stiffener in there? Oh no.
Get out of here. Yeah, Andy, could I ask another question?
Yes.
I don't want to put words in your mouth, but I'm seeing kind of two big picture themes, and you can correct me if I'm wrong, but one is the technical knowledge about structural stability, and the second one would be having a standard practice that makes it easier for you to have success in these designs. So my more specific question around that is, in terms of standard practice, would you suggest that we talked a lot about the bottom chord extension at the column line, and also of having a joist near the tip of the cantilever, but what about the bottom chord extension at the tip of the cantilever? Is that something that we should mandate, or is it just a matter of making sure you pick the right K?
I think it's a matter of picking the right K for the bottom chord extension at the cantilever. It's very rare to see a bottom chord extension at the cantilever. It's quite common to see it at the column, but very rare to see it. And it's very rare to see the bottom chord extension at the cantilever, and I think if you mandated that, you would have lots of pushback from the design and construction communities.
Okay, well, the CISC manual, the new product that came out does give that as an option. So I'm guessing that the marketplace has kind of come to the conclusion that it's easier to account for the stability of the cantilever in a different way than you'd have to have a bottom chord extension on both sides of the columns. So that would be 3 altogether. Or well, sorry, you'd have 1, 2, 3, 4 for a double cantilever.
Yes,
And then also,
usually they don't. If there is a bottom chord extension that's opposing, they usually don't. They usually loosen the bolts on the one side afterwards, after installation, so that you're not trying for continuity on your joist.
right. I get that. I mean, like along the line of the girder. So if you have one at each, let's say the double cantilever, you have one at each column, and then you have another one at the tip of each cantilever, and then potentially another one on the inside near the column. This is, I think, one of the cases that's covered in the CISC book. So I'm just wondering, like, is that not the route that we should be going?
We sometimes put in a bottom chord extension in the backspan if we have a problem with wind uplift. Generally not otherwise. And we might do that even with simple span girders, if that's the case, or if it's an edge one.
Awesome.
So a couple other questions here. I don't have Mike. UBC did not teach us Gerber Girder systems. You briefly talked about continuing education courses in BC. Talk a little bit about that. So the SEABC, which is the Structural Engineering Consultants of BC, runs an evening program for engineers, and it's meant as a continuing education or / refresher. Right now and they're usually offered as in class and in person, and they're offered after work. There's one session that usually goes 4 till 6 BC time, and one that goes 6:30 to 8:30. They're now only online, and in previous years they've been online and in person. And we do get a variety of folks from Alberta. I've had people take these courses. I had one taking one of my courses from Africa, and another one from Iceland, and variety of places that you kind of wonder why they'd be interested in designing steel for Canadian buildings, but they are offered, and I would suggest going to the Structural Engineering Consultants of BC website and looking at their certificate program. But the real problem is how do you do these courses? And when we hire people in our office, we make it a condition of employment that they take those courses. We pay for the tuition, and they're about $500 for a 12-session 2-hour course, and they put in the time and off it goes. General question to everyone here: are all you structural engineers? I'm in first year and trying to decide whether to do civil or structural. And sorry to scare you if you're in first year. But I was always, and when I hit first year engineering, I was wanting to be a chemical engineer, and then I went through first year chemistry and decided that there's no way I'm going to spend the rest of my life doing chemical engineering after that, and wound up going into civil because I wanted to do structural. And I think that structural engineering is a really interesting field, and I have looked back on it now with sort of 40 years of working and really think that was a very fortunate choice at the time. And somebody said recommend doing co-op to determine your interests. The challenge with co-op is that a lot of the structural courses are not really taught until towards the end of the program. You really don't learn how to do steel design and concrete design until you get to the end of it. So having the kind of experience that you'll get in co-op is different than the kind of work that you will do when you're practicing. And it's quite difficult to get a co-op job in the structural field in my experience. So we do hire, we have done some co-op students. Right now we have a co-op student who is partway through her master's degree. She had worked for 3 years for a consultant back east. And so she's sort of able to be up and running and going into being in the office, not quite as closely supervised. And part of our challenge right now with COVID is how to supervise people closely when you can't sort of get close to them. So, I think I answered that next question about the structural co-op. It's a difficult one to do, and at best you'd probably be, almost in your 4th year or partway through your 4th year before you were doing that, and so it's kind of difficult to do that.
Could I just maybe interject a little bit, because Michaela's asking specifically about U of A. I just briefly mentioned that we do not have a bachelor's degree in structural engineering. It's civil engineering, but to get the maximum value of somebody interested in structural engineering, you would take your electives on the structural engineering stream. So if you don't want to wait until 3rd year to get a structural course, you can, well, you would still have to wait to get the course, but you can get involved with the Steel Center and maybe get involved in some research and things like that in structural engineering to get started. But just to be clear, there is no such thing as a structural engineering bachelor's degree at the U of A. There is at the master's level.
Yes, and that's the same at UBC as well. And it was the same in the old days, and it's definitely now the same.
Awesome. Yeah, lovely. I'm just gonna see if anyone else has any other questions, because Michaela is actually part of our Steel Squad, so we could have a quick discussion afterwards. He's around.
That was a very nice presentation. Thank you, Andy. I just had a quick question regarding that vertical stiffener. What are the design requirements for that vertical stiffener? So I just wondering, what are the loads, the load path transferring?
The loads, I'd kind of look at it as though we were putting on we know the load in the column, and so we can figure out what the stress in it is and look at it from a sort of unsupported length basis. But a lot of times it just comes down to looking at minimum B over T's. And the code has minimum B over T's for stiffeners. So you tend to size them that way and kind of look at the stress on it and see whether or not it seems reasonable based on it. Usually you've probably got, it's usually not an enormous number. It's like 700 kilonewtons or something like that coming down on a column, and because it's only the roof loading. So Savon, of course, had more loading than you normally get because it was parking on the roof. So you had concrete on metal deck. A lot of these Gerber systems tend to be just the metal deck with some insulation and roofing on top of it.
Actually, that vertical stiffener is not meant to stiffen the girder web, right?
Yes.
It,
Yes.
mhm.
No,
It
is
is
meant.
part of, okay, it is a part of like extension of the column above, right? To
Well,
transfer the vertical load from the roof to column, right?
So hang on, where I had the 3 photos here. So that there you can see. I mean, what's happening here, and because it didn't have a vertical, it didn't have a bottom chord extension, you are sort of looking at trying to do the 2% force, and can you take the 2% force, and if you try putting a point load of 2% here of the axial force, you find that the web is not very happy at all, and having the stiffener in there does solve that. But fundamentally, this is a twisting over of the web of the girder, and it is really important from the point of view of web crippling at the column. And it's kind of interesting that there have been 2 really significant structural failures in Vancouver. The first was the Second Narrows Bridge, and the second was the Savon. And in both cases, it was web crippling where there was no stiffener at a point load that was the main cause of that failure.
I see. Okay,
So,
so
and it's a very inexpensive fix. They can nowadays with modern beamline construction and things like that, the stiffener can go in very easily, and it does really improve the performance.
yeah, that's true. Okay, so actually those stiffener are not because of the shear, because we also use some vertical stiffener in the web of the steel plate girder for shear as well. These are not for that
No.
purpose. I see.
No.
Okay, it's just for the vertical load.
I agree. It's just for the shear stiffeners on sort of the old plate girders that every railroad bridge in Canada had in the 1900s. The engineers there had figured it out. They could have thinner plates if they had the web stiffeners. Is not because of that. We're not trying to improve the shear performance in there. We're trying to improve the critical, the buckling at the point load.
I see. Okay, thank you. Thanks.
And trying to make our girder not look like this one here.
Sure. Thanks. Thank you.
Good.
Awesome. Thanks for that question, Morgan. Any other questions? Okay. Seems like that's pretty much it. So I'm just trying to stall here to see if any questions pop up. But yeah, okay, sweet. Well, thank you everyone for attending today. This was a really good presentation. Thanks, Andy. And we had lots of people saying that they really enjoyed the presentation as well in the chat there. So it was really good. Thank you so much.
Good.